Hello, I'm Andrew. Welcome to Magic on Every Level, distributing magic throughout the stack. Today, we'll look at the magic latent in the web technologies we take for granted. We'll look at an implementation framework to inform where and how we harness this magic. Then we'll look at several implementations from William and Mary, explaining where, how, and why we implemented each as we did. Before we jump into the implementation framework, I'd like to acknowledge one of my favorite songwriters, Sam Phillips. Her song, Magic for Everybody, inspired this session's title and overall concept. That concept being the simple, seemingly mundane technologies we take for granted truly have magical potential. At the very least, as our constituents interact with our sites, we can bring a smile to their faces each time they successfully find information, complete an application, or accomplish their objective. Now, let's tackle our implementation framework. At the highest level, the framework has 3 steps. Let's take a look at each step and apply it to William and Mary's web environment. To begin, we're not trying to solve a problem or implement magic. Instead, we're trying to understand our web environment or web stack to discover its latent magic. Step 1. Enumerate every element, service, or technology in our web environment by the role it serves. Feel free to adjust the groupings to your liking. These are the roles that make sense to me. Content management, that is, systems where code and content are managed. Content servers, these are systems from which code and content are served. Intermediaries would include any systems that mediate client requests for code and content. Clients, the end user systems that request and interpret code and content. And finally, feeds. This is a catch-all for ancillary systems that provide subsidiary content for one of our other systems to process. It's an arbitrary distinction to separate feeds from content servers, but I find it helpful, particularly in tracking third-party systems or systems controlled by other departments that aren't part of our team's web stack. Let's take a stab at enumerating the elements of William and Mary's web environment within these 5 roles. Within William and Mary's content management role, we obviously have Cascade CMS, which is where we manage the majority of our public content. We also have a GitLab repository server where we manage certain technical assets. And finally, we list a collection of AWS, EC2, Linux, Apache, and MySQL, which together make up the cloud server infrastructure hosting both Cascade CMS and our Git repository server. Our content servers include additional AWS EC2 Linux containers, this time configured with Apache and PHP to serve Cascade published potentially dynamic code and content, plus an AWS S3 bucket, to which Cascade and our GitLab server publish certain static files, and from which those files are served. We have one intermediary system, CloudFront, which is Amazon's globally distributed reverse proxy and cache system that sits between our content servers and our clients. Our clients include all of the various operating systems and browsers that our end users employ for requesting, receiving, interpreting, displaying, and managing interactions with our code and content. And finally, feeds. As previously described, these are systems external to our team's web stack. They might include XML-based feeds like RSS, Atom, and CAP, JSON-based feeds like JSON and JSONP, or other types of feeds, for instance, iCal. As examples, I've listed 3: RSS from William and Mary News, JSON from William and Mary Events, and XML from the Rave Emergency System. In completing step 1, don't let perfect be the enemy of progress. If you've left something out, you can come back and add it later. Once we've completed step 1, it remains complete until something changes or we find a system we've overlooked. Moving on to step 2. Analyze these elements to ascertain their latent magic. Our goal in this step is to explore each element captured in step 1. Warham's law states any sufficiently advanced technology is indistinguishable from magic. It's in this sense that we want to define the types of magic latent within our systems. Here's one approach to analyzing each of the elements in our web stack, which we enumerated in step 1. Strengths: what are the native capabilities of this element? What things was it designed to do? Possibilities: what could this element do reasonably well? Either secondary capabilities or any capabilities that can be repurposed. Weaknesses: what things does this element struggle to do? These are technically possible when absolutely necessary, but may simply be inefficient or could possibly be truly bad ideas. Irrelevancies: what things are outside the scope of this element? Obviously, we aren't looking for an exhaustive list of everything we can't do with this technology. Instead, we document anything specific or general that we found surprising, confusing, or less widely known. Let's analyze a few elements of the William and Mary web environment. In deference to time, we can't discuss all 4 metrics for the 10 items derived in step 1. Instead, we'll provide a few exemplars for clarity. Beginning with the content management role, let's take a look at Cascade CMS as an example. For Cascade's primary strengths, I've included managing, transforming, and publishing web content, and managing and authorizing editors of web content. Possibilities within Cascade might include simplifying and automating Cascade editor experiences, creating workflows for content creation, updates, and approvals, and providing an API to customize content management interactions through web services. Its weaknesses might include integrating external code-centric programming tools, for instance, IDEs, Git repositories, and the like, or dynamically updating content pages from often changing external feeds. That is to say, updates to feed-based content are not immediate and require pre-scheduled or manually triggered fetch of the feed, followed by publishing of the affected content. Irrelevancies. Web content hosting and serving. Cascade CMS uses a content publishing paradigm. It isn't intended to serve our content directly to the public. Likewise, client interaction with published code and content are out of scope. Again, Cascade CMS doesn't directly interact with the public. Moving along to content servers, let's look at our AWS, EC2, Linux, Apache, and PHP setup. Its primary strength is dynamically executing code upon each page request. That's what PHP does. Possibilities include modification of HTTP status, errors, and redirects, get and post parameter processing, session management, and access to the file system. Weaknesses of PHP we might want to remain aware of include being unable to process PHP within Cascade internal page previews. Additionally, there's a trade-off between dynamic processing on the content server versus caching results in CloudFront. Irrelevancies, content management and content caching. Of course, both content management and content caching are available for PHP, but we don't offer them in this environment, as we cover those functions elsewhere in the stack. As an intermediary, we implement Amazon's CloudFront service. Its strengths include reverse proxy and cache functionality. Possibilities available include resource mapping by path, cache directives by path or file type, passing or blocking get parameters by parameter name, and caching separately by get parameter value. Weaknesses worth noting might include some types of server responses preclude caching. If you use CloudFront, you might make note of such caveats found in the documentation. Additionally, there's a trade-off between dynamic processing on the content server versus caching results in CloudFront, as we noted before. As for irrelevancies, we might note that CloudFront doesn't provide content management, doesn't dynamically interpret code or content, has no direct file system access, and no database connectivity. With regard to clients, I'll give a shout out to Google Analytics and caniuse.com. At William & Mary, Google Analytics lets us know what browsers our constituents utilize, and caniuse.com lets us know the capabilities of those browsers. Our institution can then determine the adoption threshold required for utilizing or deprecating browser capabilities. Hopefully, if I've provided enough examples for you to see how, in this step, we've more deeply documented our web stack. Once we complete this analysis for each of our systems and technologies, we've completed step 2. This analysis remains complete until something changes or we find systems and or functionality we've overlooked. Now, finally, we reach step 3. Ask good questions, get good answers. We don't actually arrive at this step until we're assigned a single specific implementation goal, which we'll tease apart and determine how to accomplish. As an aside, the implementation framework doesn't address why a group wants this functionality or what priority the implementation will receive. These discussions are out of scope, but they are important. Someone needs to make those decisions, and they need to do so before we're assigned this goal for implementation. So once we have an implementation goal, we need to decide where and how to build new magic. I assert the quality of our decision is impacted by the quality of the questions we ask. To that end, here are 3 sample questions we might ask. First, what is the one specific goal we're trying to accomplish? Sometimes we receive goals with an unclear objective, having too much extraneous information. For instance, we're not ready to discuss details of the UI/UX interface. Instead, we want a succinct statement like, provide this user group the ability to accomplish that task, or make it easy for this user group to find that information. Second, we ask at what level within our web environment do we have magic that could accomplish this goal. Here, we we want to identify all of the services and technologies across all levels of our web environment within which we could theoretically implement a solution to meet the goal. Sometimes we find the goal can literally only be met at one level or with one technology. Other times we find several levels at which the goal could be met. Finally, we ask, given our understanding of the roles and services within our web stack, as well as the strengths and weaknesses, which one is the best alternative? Aha, now we get to make a decision. We've collected all the raw data, but how do we come to a final answer? Let's evaluate two aspects. First, what criteria establish one alternative as the best? Maybe the speed and simplicity of implementation are key. Maybe you need efficient server processing or efficient client processing. There's not a single right answer. Your institution has different constraints on human, server, and client resources relative to other institutions. You need to narrow the criteria for what best looks like in your situation. Likewise, there are various processes for making a final decision. Maybe you like spreadsheets, a row for each option and columns for pros and cons. Alternatively, you might prefer group consensus, a team meeting where you walk through each option. Or you can do both. Take your spreadsheet to a team meeting for discussion leading to a consensus. Regardless how you define best or your process of deciding, you need to make a decision. You determine where within your web stack, with which services or technologies, you'll integrate new magic to accomplish this one specific goal. Enough already with the theory. Can we please see some concrete examples? Absolutely. Let me share a few successful implementations from William & Mary. For each, I'll summarize the specific goal, where and how within our web stack we implemented some magic, and the logic and reasoning behind why we implemented each as we did. I won't scroll through pages of code, much of which is dependent upon our unique web environment. Instead, I'll present the 50,000-foot view of each project. In most cases, knowing the where, how, and why is enough to implement something similar. Nevertheless, if you need reference code for a particular example, feel free to email me. Let's start with an example with few implementation possibilities, all within one layer or role in our web stack. We're going to automatically adjust Cascade transports when we clone from production to test. When we clone Cascade to build a test instance, for example, to try out a new version of Cascade, we adjust the transports to prevent the test instance from publishing to production web servers. That would not be ideal. The objective is to minimize the number of adjustments we must perform manually, thus mitigating the chance of human error. Where must this magic happen? Since we want the transport adjusted prior to launching the test instance, it can only happen at one layer of the stack, that is, content management, Linux Apache MySQL system. That's the server environment on which Cascade runs. I came up with two options. One, we could modify records in the MySQL database. We could find the transport path record and replace www/cascade-prod with www/cascade-test. Alternatively, we could modify the drive paths in Linux. We could either melt, map, or symlink a virtual path as a pseudonym for the actual destination. For instance, we could provide a single path like www/cascade, and on the production Linux server, it would point to www/cascade-prod, while on the test Cascade server, it would point to www/cascade-test. As long as the virtual path that Cascade transport uses is functional, Cascade neither knows nor cares about our tomfoolery. Our choice? Well, we decided to modify the paths in Linux. Why? Comfort and simplicity. Our server colleagues in IT were comfortable with the solution and found it easy to implement with their container build process, but either solution would work just as well. Here's another example where only one layer of the web stack is a reasonable implementation option. I'm going to provide spam protection for mail-to links within our WYSIWYG content. We sometimes have need to place mail-to email address links in line within our WYSIWYG portion of our content pages, but doing so in plain text makes those addresses low-hanging fruit for every dumb code-scraping spam bot on the internet. Therefore, we want to do this in a way that thwarts dumb spam bots from collecting our email addresses, while simultaneously making it easy for our content editors to implement. Where must this magic happen? Our only viable choice was within the web browser after loading the page. Doing so any earlier provides no benefit, as the page delivered to the user or spam bot would already contain the email address in the page's source code. Here's what we came up with. Implemented in JavaScript, the content editor places a user ID in two sets of square brackets, like so, which will transform into a mail to link like this. An optional comma allows the link text to differ from the mail to address, and an optional prefix will change the email server to one of our approved mail domains. Implementation details. After the page renders, we use JavaScript to scan all content sections by ID or class name, and use regular expressions to search for a double square bracket notation. We replace the match text with an appropriate mail to link, as described before. Could we do this another way? No. Well, with two caveats. We could have used something other than square brackets, still implemented in JavaScript, or we could use a form mail type solution, which would be a hybrid content server plus browser solution. That was out of scope of our system at the time. The point is, any transformation that renders a valid email address prior to the content delivery to the client results in raw HTML page code containing a valid address, which even the dumbest spam bot would collect. Our third example could be implemented several ways, at completely different layers of our stack, with a few caveats. I wanted to embed a YouTube video within our WYSIWYG content. We have some need to place YouTube videos in line within the WYSIWYG portion of our content page, but we want to do so without having to later edit the code on each page when YouTube changes its embed script or API, while simultaneously making it easy for our content editors to implement. Well, where would such magic happen? Theoretically at any level, but in practice, anywhere except CloudFront, simply because CloudFront doesn't provide a tool to do this. Here's what we came up with. We decided to use a double set of curly brackets or braces, partly because of its similarity to the magic double square brackets for email protection that our editors already understood. Specific format is a bit more complicated, but easy enough to cut and paste from our Cascade help page, and then tweak as needed. This is what it looks like in the Cascade help page, and then a specific example for Sam Phillips' Magic for Everybody. As far as implementation details, we chose to use JavaScript since we were already performing a similar transformation for email addresses. After the page renders, we use JavaScript to scan all content sections by ID or class name. We use regular expressions to search for a double curly bracket notation. Replace the match text with a JavaScript function call to our stub function, the latter being maintained in a common JavaScript library file and implementing YouTube's current embed script or API. Could we do this in another way? Yes, we could do the transformation in velocity. This would shift the processing load of the transformation from the client to the Cascade server, while still allowing us to maintain the transformation function in a single place. Could we use PHP on the content server? Yes, but it's not the best option. It has all the benefits of the velocity solution except one. Unfortunately, PHP functions do not execute or render within Cascade page preview. In this case, using PHP has a substantial loss of functionality, no page preview, without providing particular benefit not available in the other two solutions. Now let's look at an example where PHP does provide tangible benefit. We want to update a site's header and footer without republishing all pages. Republishing some of our sites can take from hours to days, and in the interim, modifications to the header and footer would be inconsistent across pages. We want headers and footers to update simultaneously and virtually instantaneously without requiring all pages to be republished. Well, where would this kind of magic happen? It's actually split between Cascade and our content servers. Here's what we came up with. Each site has its own header and footer, and these are Cascade pages as opposed to blocks, meaning they can be published directly to the content server as standalone .php files. Why use PHP? Because Cascade publishes the header and footer as separate files, we can include them dynamically as each content page is requested. We can edit and publish the header and footer independently, and all content pages will begin using the updated files immediately, without requiring us to republish every single content page. How do we implement such magic? Within Cascade, for page preview, two system view internal sections of velocity code include the header and footer Cascade assets, respectively, within the content page being previewed. External to Cascade, when published, two system view external sections of PHP code include the header and footer.php files, respectively, within the content page sent by the content server. Are there any downsides? There's only a small increase in complexity maintaining the internal versus external code sections as well as minimal PHP code. Is there any other way to do this? We didn't find any other practical way to do this. Keeping the full process in Cascade requires republishing all of the pages. Trying to assemble the header and footer using, for instance, asynchronous JavaScript queries could leave a content page without primary branding and navigation for some period of time. The next example is the most recent implementation of those I'm showing you today. We call it pages of stacked rows. Our designers and content specialists want pages containing multiple semi-independent sections of content stacked one atop the other in a vertical fashion. Where would this magic happen? The rows of content will obviously be managed within Cascade, which provides multiple options for doing so. Additionally, we have options for how we preview, publish, and assemble these pages of stacked rows. What are some of the alternatives? The first option is a single complex data definition with the repeatable row region containing a row type selector, which uses selector-dependent conditions to display the appropriate fields. Pros and cons. The complex data definition option has the fewest number of component assets per page, just one. But there's quite a bit of complexity in the conditional display of fields depending upon row type, particularly if you have dozens of row types. Additionally, rows in this scenario are not reusable components. Placing the same row on multiple pages, for example, a Google map to the admission office, requires rebuilding it on each page. A second option is a data definition with a repeatable block chooser, where each row is a block with its own data definition, potentially a separate data definition for each type of row, all assembled into one publishable page by velocity. Pros and cons. So the block chooser option adds complexity by requiring each row to be built separately as its own block prior to placing it onto a content page. Benefits include less complexity in both data definition and conditional display of fields, since every row type could have its own data definition and asset factory. Additionally, rows become reusable blocks that can be placed on multiple content pages. But each of those content pages would need to be republished whenever the block is updated. Finally, we have a data definition with the repeatable page chooser, where each row is a page with its own data definition, potentially a separate data definition for each type of row, all assembled into one publishable page by either velocity and/or PHP. Pros and cons. The page chooser option is very similar to the block chooser option. The chief difference is when each row is a page, it can be published to the content server. This means a content page of rows can be assembled by the content server using PHP, which also means that all content pages using a shared row will automatically be up to date as soon as the row is republished. No need to republish all of the content pages that use this row. Well, which do we choose to use? We chose the page chooser option. Why? We had three main reasons. We expected to have dozens of row types, which makes managing of a single data definition utilizing conditional display of fields daunting undertaking. We expected a number of specific rows to be repeated or shared across content pages. And we expected some shared rows to be used across departments, where a row owner is unable to publish all related pages after making changes to the row, which could leave stale content for up to a week until the next full publish of the affected site, unless the content owner from the other department republishes the page. As far as implementation details, well, as with the previous header footer example, we use a system view internal section when previewing the content page with all rows, and a system view external section to write a PHP include statement for each row when publishing. Could we do this any other way? Absolutely. Our decision may not be your best option. Your circumstances might dictate using one of the other options, maybe because you expect to have fewer row types, or you don't expect much sharing of rows across content pages. Our penultimate example shows how we manage a hybrid news setup between the university's news and media team building their stories in WordPress and our academic units building departmental news stories in Cascade. So, borrowing news stories from WordPress. Well, our university's central news and media team uses WordPress to manage their stories. Our academic units build their departmental news within Cascade, and the latter group would like to borrow stories about their respective departments from the WordPress site into their departmental news feeds. Well, where could we make this kind of magic happen? Well, theoretically anywhere, but most likely Cascade, PHP, or JavaScript. Here's what we came up with. We implemented a hybrid solution using Cascade and client-side JavaScript. As far as implementation details, well, on the Cascade side, a department's content editor builds a borrowed story asset in Cascade, which contains the URL of the WordPress story to be borrowed. Cascade creates the page, placing asynchronous JavaScript code in lieu of content. On the client side, JavaScript fetches the data and places it appropriately within the page template. Likewise, for departmental news listing pages, Cascade can build the listing with all the details of the stories hosted in Cascade and stub items for the external stories, which the client will replace using asynchronous JavaScript when rendering the page. Could we do this any other way? Well, theoretically, PHP would work in place of JavaScript, but as mentioned before, the results won't be available in Cascade page previews. Alternatively, we could try to use Cascade exclusively without JavaScript, but that would likely require triggering an update of the feed before publishing, plus any changes in WordPress like typo corrections require a refetch and republish before they would be reflected on our content servers. In this final example, we build an exclusively PHP implementation without any equivalent page preview, in fact, without any Cascade pages at all. We call it a highly functional 404 page. We had several goals for this project. First, catch deprecated paths and redirect them to a new location. For example, our office was called Creative Services, and now it's Web and Design. In the process, our website's path changed. Second, we want to support vanity or shortcut names for departments and projects. For example, www.wm.edu/cascade takes you to our Cascade help pages, which actually live within the Web and Design website. And we also want to catch all the other page not found errors and show search results based on whatever we can parse from the URL. Where would we do this kind of magic? Well, exclusively on the content server. Cascade doesn't receive interaction from clients of our published pages, and clients don't have access to all of our parsing and redirect rules. Here's what we came up with: a pure PHP implementation. Literally, a file called index.php that we upload into Cascade and it publishes to the content server. No Cascade pages, data definitions, or anything else. As far as implementation details, well, we're on the Apache PHP server. Cascade publishes this file, and then Apache catches any 404 requests and sends them internally to this PHP file. PHP looks up the path to see if it's a deprecated or vanity path. If it finds a match, it redirects. And if not, well, it searches the URL for any words it can find, puts them together as the query string for a Google search, and sends a page with Google search results to the user. Could we have done this any other way? Not really. Well, the final piece could have been a Cascade page, but all of the processing would still need to be done in PHP, and the Cascade page would simply provide a Google search. That's all of the examples I have time to share in this session. Hopefully, they've illustrated how to utilize an implementation framework and provide food for thought as you tackle your own upcoming projects and goals. Now it's time to start wrapping things up. Caveat magus, let the magician beware. Step 3 isn't the end, it's the beginning. The point of having an implementation framework is to help you decide where and how to implement new magic, with an understanding why this is the best option. It doesn't replace the hard work of writing code, working with designers and content experts to tweak the UI and UX, or performing testing and QA. The framework doesn't remove the burden of actually doing the implementation, but it might just prevent you having to do the implementation twice. Let me close with an exhortation from Tennessee Williams. Yes, I have tricks in my pocket, I have things up my sleeve. I am the opposite of a stage magician. He gives you illusion that has the appearance of truth. I give you truth in the pleasant disguise of illusion. Let's go build websites and view them with magic at every level and present truth in pleasant disguise. Thank you for listening. Bye-bye.